Granola bars. The following table shows the fat content in grams and calories for a sample of granola bars. I'll read the data in the table. The first number will represent fat and the second number will represent calories. 7.6 and 370, 3.3 and 106.1, 18.7 and 312.4, 3.8 and 113.1, 5 and 117.8, 5.5 and 131.9, 7.2 and 140.6, 6.1 and 118.8, 4.6 and 124.4, 3.9 and 105.1, 6.1 and 136, 4.8 and 124, 4.4 and 119.3, 7.7 and 192.6. Use technology to make a scatter plot of the data. Use fat as the independent variable x and calories as the dependent variable y. Does there seem to be a linear trend to this data? The technology I'm going to use to demonstrate the scatter plot is StatCrunch. The data has been entered into StatCrunch with one column representing fat and the other column representing calories. To create the scatter plot, we come to Graph, we select Scatter Plot. For the x variable, we will choose fat, and for the y variable, we will choose calories, and then we'll click Compute. And StatCrunch generates a scatter plot for us, and we can see from the scatter plot that yes, there does seem to be a linear trend to the data because there seems to be an upward trend with the data points falling roughly along a straight line. Compute the correlation coefficient and the regression equation using fat as the independent variable and calories as the dependent variable. Again, I will demonstrate how to do this using StatCrunch. To find the correlation coefficient and the regression equation, we come to Stat, choose Regression, Simple Linear. For the x variable, we'll choose fat. For the y variable, we'll choose calories, and then we'll click Compute. The output will have a lot of information on it, some of which we don't really need. We just need to find the regression equation and the correlation coefficient. So here we can see a correlation coefficient of 0.713, and here we can see our regression equation. Calories is equal to, rounding off to one decimal place, 62.0 plus 15.2 multiplied by fat. So using StatCrunch, we found our correlation coefficient of 0.713 and our regression equation. What is the slope of the regression equation? Interpret the slope in the context of the problem. The slope of the regression equation is a number in front of the independent variable. In this case, the slope is 15.15. Interpret the slope in the context of the problem. So remembering out from algebra, the definition of a slope is the change in the y variable, in this case calories, divided by the change in the x variable, which in this case is fat. And our slope is 15.15. So to interpret it, sometimes it's easiest to write this as a fraction. So we'll write this with a denominator of 1. So what this means is each additional change of fat in 1 gram results in an associated change in calories of 15.15. So each additional gram of fat is associated with an increase. It's an increase because the slope is positive of 15.15 calories. What is the y-intercept of the regression equation? Interpret the y-intercept in the context of this problem, or explain why it would be inappropriate to do so. The y-intercept of this equation is 62.0, and the y-intercept represents the y value when x is equal to 0. In this case, it would be inappropriate to interpret the y-intercept because in our data set there were no granola bars containing an x value of 0, in other words, 0 grams of fat. Find and interpret the coefficient of determination. The coefficient of determination is r squared. You can find the coefficient of determination by simply going back to the StatCrunch output, or you could take a calculator and take our r value of 0.713 and squaring it, giving us a result of 0.509 or 50.9%. What this means, if we interpret the coefficient of determination, that means that about 51% of the variation in y, in other words, 51% of the variation in calories, can be explained by the fat content. Use the regression equation to predict the calories in a granola bar containing 7 grams of fat. Our regression equation is calories equals 62.0 plus 15.15 times fat. And so to answer this question, we replace the variable fat with 7. And so the number of calories would be 62.0 plus 15.15 multiplied by 7, giving us a result of about 168 calories. Would it be appropriate to use the regression equation to predict the calories in a granola bar containing 25 grams of fat? If so, predict the number of calories in such a bar. If not, explain why it would be inappropriate to do so. When looking at our data, the maximum value was 18.7, and so 25 is outside the scope of our data, and so it would be inappropriate to use the regression equation because there are no granola bars in our sample with 25 grams of fat. "25" is outside the scope of the data. Looking at this scatter plot, there is a granola bar in the sample that has an extremely high number of calories given the moderate amount of fat it contains. Remove its data from the sample and recalculate the correlation coefficient and regression equation. How did removing this unusual point change the value of r and the regression equation? So if we look at our scatter plot from before, we see that most of the data lies within this band, except there's this one unusual data value It has around 7 grams of fat, but over 350 calories. So what we're going to do is we're going to go back into StatCrunch and see if we can find this unusual bar, remove it from the data, and then recalculate the regression analysis. So we'll notice that the first row of our data value contains a bar with 7.6 grams of fat and over 350 calories, 370 calories in fact. So this is our unusual data value. So we're going to remove it from our data and we're going to recalculate the regression. So stat, regression, simple linear, with an x variable of fat and a y variable of calories. And now what we're going to look at is the effect on R and on the regression equation. So now our new correlation coefficient is 0.976. So our correlation has gotten stronger. And our new regression equation is calories is equal to 55.84 plus 13.76 times fat. So we can see that removing that unusual data value gave us an R value of 0.976, so R got stronger. And in our regression equation, calories is equal to 55.86 plus 13.76 fat, we can see that our y-intercept and our slope were changed as a result of removing the data value.